Yeah, it was my pleasure to get invited to be speaker at this occasion. And today I'm very happy to tell you about our recent progress in the ultra high fidelity and scalable quantum processors based on the Fluxonium qubit. So it looks like I look at the schedule. It looks like I get plenty of time, like 1 hour. So I will spend a little bit of time for the introduction, and then hopefully we'll leave enough time for plenty of time for questions. Yeah. So to introduce the motivation, so here I'm just picking two instances for as applications for the scalable quantum computer. So people are always talking about doing quantum simulations to solve the hardest chemistry problem, or breaking this very secure encrypted code like the ISA using a quantum computer. But according to a recent analysis, so the resources to perform such a huge computation is huge. So, for example, if we want to simulate the energy level or the chemical reaction regarding this compound, which is a cofactor that's commonly used in fixing nitrogen, or in some other terms, it's a very useful compound to make fertilizers. And to do that, people estimated that for a physical qubit error rate of 10 to the minus 3, we actually need 180 million qubits to perform a precise enough simulations that it's relevant enough for our applications. And the things get much better for the lower error rate or physical error rate for 10 to the minus 6. So the total physical qubits reduced to like 1.3 million. Still, it's a huge number. For another example is that to break in the ISA, which is now commonly we use the 2048-bit ISA. To run strong algorithms to crack this code with only 10 to the minus 3 physical qubit error rate, the total qubit amount requires is on the order of 20 million. So if you look at this number, it looks totally hopeless. And so the main message is that to run large applications or any applications that's relevant for today's commercial or relevant application. So you need really hundreds or thousands of logical qubits, and that means that with even we break the thresholds of the surface code, which has the highest threshold we know now, we still need millions of physical qubits. So one slightly relieving message is that this number keeps reducing as people advance the field of quantum error correction. So my colleague Chunqing told me that at 10 years ago, so this number is like 200 million or something like that. So it's already reduced by the huge factor, but it's not enough, but we still anticipate that it's going to be reduced by smart people working on algorithms. Okay, so the main message is that we need logical qubits. So by building logical qubits, we need to get a very low error rate, and then in terms of getting lower and lower error rates. So one benefit is that from this paper published by Austin Fowler and the co-authors, as the physical error rate goes lower and lower, the overhead of building a logical qubit or doing the fault-tolerant quantum computing also reduce. So here we can see that if we want to have a logical error of 10 to the minus 20, which is looks very low, but it's not that low for a large application. So with only the factor of 10 below this the error threshold, so we still need like thousands of qubits. But if we go another factor, so another factor of 10 lower in terms of errors, and the numbers of qubits get reduced by the large amount. So that's one motivation to basically go into the lower error rate. Another more important motivation is that if you look at this curve on this end, when the error rate, the physical error rate of our qubit is high, approaching the threshold, you can see that the number of resources required to run a perfect quantum computation basically diverge. So it means that if we don't go below the threshold, or basically go low enough below the threshold, we're not going to so anything we're going to do is not going to be useful, because because the error just adds up. Okay, so in this graph, and then it at least tells us that lower error rate is very useful, and then there must be the threshold that we have to go definitely go below that. And although the surface code threshold is something like 10 to the minus 2, but recent experiment indicates that it is still not enough. So that motivates us to define a slightly different path than anybody else, which I called it fidelity first and scale up later. So this is a graph that everybody knows, and then which is originally made by Google, and then there is I think highly acknowledged or accepted path that the people can start scaling up the system at the same time as reducing the errors. However, so we think that it actually makes it's actually worth to try another a little bit different path. That first we reduce the threshold, or sorry, we reduce the physical error of a qubit below 10 to the minus 3, and then try to build quantum error corrections on their level to see what's happening. And then once we see that that's a sign of success, and then we start to scale up the system. So that's what we are going to do. Okay. So with that, with concentrating or trying to reach a higher fidelity as our core strategy. So I'm going to introduce a Qubit type, which is called Fluxonium, as the Qubit platform we choose to realize our strategy. So Fluxonium Qubit, it's actually invented in 2009 by Professor Manouchian, who is currently a professor in University of Maryland, and Professor Michel Devoret in Yale. So this qubit has a few very interesting properties that's good for high fidelity applications. So first, it's a superconducting loop without isolating island. So if you look at the qubit, so it has one junction and a junction array. So normally people just tend to approximate the junction array as a piece of superinductance. So in this kind of approximation, if the junction array or the junction in the array is large enough, and we can kind of think it as the same piece of metal, but with just very high inductance. So this kind of circuit constitute a superconducting circuit without isolating island. So that's very different from the transmon or the charged qubit, where you actually have two different islands where the charged particles can tunnel back and forth. So this property actually gives rise to insensitive to charge fluctuations with large anharmonicity. So this reflects in the top plot here. This plot, so people actually the co-author Yanfei and co-author compare with a bunch of different kinds of superconducting qubit across transmon, flux qubit, fluxonium, and whatever they call quantum. And then they find that Fluxonium actually has a very large anharmonicity because of these properties, and then transmon also it's a promising candidate that's insensitive to charge fluctuation, but but instead of using a superconductance suppressing the charge tunneling, the flux transmon actually use a large capacitors to suppress that, which give rise to a low anharmonicity. So you can see that transmon, the anharmonicity is quite low. And then on the other hand, the Fluxonium wins both in these two aspects. So large anharmonicity and insensitive to charge fluctuations. And then another interesting or important prospect of Fluxonium is that it's actually the low frequency qubit. So here in these two plots we can see that the horizontal axis is the frequency of the qubit, and then why the vertical is anharmonicity or the T1. So T1 is the coherence time. So Fluxonium is always on the left side, so which means that its frequency is low. So it's sometimes people don't like low frequency because it means that the thermal excitations are negligible. So it's important. But the good side of having the low frequencies is that it is actually has less impact from dielectric loss. So here I'm just drawing the a calculation of dielectric loss, the impact of dielectric loss to coherence times in this plot on various qubits. So we can see that there is a trend that the dielectric loss has less impact on low frequency qubits simply because the low frequency at lower frequency, so the microwave or the radiation oscillates lower inside the material. So it we compare with the so oscillating slower in the material compared with the rate of energy dissipation inside the material. So by just having lower frequency, so to have the frequency or have the qubit oscillating slower, we actually can go higher coherence. Even we don't improve the dielectric loss. We don't improve the material at all. So this is already demonstrated that people can achieve like 1 millisecond T1 and T2 times with qubit at very low frequency, so something around 200 megahertz, which is more than 1 order of magnitude higher than the transmon qubit in terms of coherence times, but in terms of energy, it's also 1 order of magnitude lower. Okay, so that's one good aspect of this qubit. And finally, so it has a superconductance, so I introduced before, and as a result of the large inductance, it actually suppressed the impact of flux noise. So in this 1 millisecond T1 and T2 times observed in the Maryland group actually are performed at the flux insensitive point. But people may ask how does the qubit perform when it is operated at flux sensitive point? So because of the large inductance, even though the flux noise might not be reduced, the T2 times is actually still larger than 1 microsecond. So and I will go back to this later because this 1 microsecond actually doesn't seem to be very promising, but it turns out that the noise spectrum density is somewhat like 1/f that can be dealt with by dynamical decoupling. So I will show you that this number is actually not that critical, and having T2 greater than 1 microsecond is actually good enough for high fidelity applications. Okay, so here I already tell you a lot of nice stories about this type of qubit, but why people are still not working on this? And why is not everybody working on that? I should say. So at least we are working on that, but not everybody. So there's still some challenges, or quite a lot of challenges on working on this qubit. So one is that so I formulate them into 5 questions. So the first question is that can one make high coherence qubit? Can one make this high coherent qubit reliably? So you might you might be able to make it once or twice, and can you always make it reliably in a multi-qubit processor like 10 qubit, 10, 20 qubit, or 100 qubit? So that's a big question. And the second one is that is it easy to read out? So it's a low frequency qubit, and then it certainly has trickier things to deal with when you in terms of performing readout. And then another question people definitely will ask is that can you reset the qubit? Because the qubit is actually in a lower frequency that's lower than the thermal fluctuations of the environment. And then this results that the qubit, if we don't do anything, it's going to be end up in the thermal equilibrium state. So we have to always reset the qubit to make it work. Otherwise, it's not going to be used as a useful resource for quantum computation. And then fourthly, so another question is that can one still do fast gates, especially 2 qubit gates on this qubit when the energy is lower? That's not apparently a yes answer. So especially to make 2 qubit gates, we really want to make the 2 qubit gate fast. Otherwise, that we don't win by having long coherence. So that's another question. And finally, so all this adds up, and then one may ask, then can you scale up this system like transmon qubit to build at least like more than 100 qubit processor? And all these are challenges that remains to be solved. And hopefully in this talk, and then I would. So in this talk, I will show our progress towards to answer all these questions, and then hopefully in the end, you are convinced by me that this is going to work. Okay. So lastly, before I enter into the technical details, so I would spend a few minutes on this slide to introduce our methodologies in approaching this high fidelity problem. So we really think that high fidelity is systematic. It's a system engineering project. So although it looks like it's just one number, so we want to get our qubit physical error rate down to 10 to the minus 3. It's 10 to the minus 3. It's just a number. However, this number actually composed of many things. So if we just decompose this number into just 2 numbers, we can say that the error of a certain quantum operations, no matter whether it's readout or gate, it is limited by the gate time, so the operation times, the times it takes for performing the operations, and the coherence times of the qubit during the operation. So in the ballpark, you're not going to have a much lower errors when you can only perform like a limited number of operations within the coherence times. So to get the high fidelity high, or to get the error low, we have to increase the coherence times while at the same time reduce the operation times, or basically reduce the ratio of these two. Okay, and then someone might already find that these two things are basically the trade-off. So it's a conflicting part of in the physical system. So if we want to operate fast, so you kind of need to entangle or couple your system, your quantum system, to the environment or to the external apparatus strongly, so you can do these fast operations. However, if you do these fast operations by coupling strongly, normally one will couple to the environment, so those unwanted degree of freedom strongly as well. So that's mess up the coherence times. So these two, we find that these two are very conflicting and contradicting parts, and it is very hard to improve these two numbers, or to improve this ratio at the same time without running into some kind of trade-off. And to do it systematically, or to make sure that we don't run into trouble, we try to solve the problems in all the aspects simultaneously, and try to divide them into orthogonal aspects. So we make sure that we don't solve one problem but mess up the other problem. So then we push these three directions at the same time to solve our problem. So one is on design and simulation, which is make sure that our qubit is robust to coherence and control errors. And then the second one is about material and fabrication, which is to make sure that we can make as clean device as possible with low intrinsic noise, and then we have as long coherence times as possible without trading off the gate time, so without messing up the control. So and then certainly, so we improve our quadratic environment by measuring some metrics. So and then control fidelity, and develop new benchmarking methods to make sure that once we make the first two things right, and then we can do the whole things. And then we can have a good control, and then we can benchmark it. And then what's more, or the most difficult thing is that all these things have to work at the same time. And then in my experience, it's quite difficult. Okay. Now, so enough about the methodologies. Then I'm going to start one by one to introduce what we do to improve things in terms of design, simulation, fabrication, and characterization. Okay. So first about the design. So our goal is to have a very high fidelity operations, and then make sure our system has low error. So this is kind of a very high level goals. Then it's not directly converted to the design layout, or whatever we fabricate and whatever we make. So normally to optimize our layout in terms of reaching a high fidelity or reaching the specific goals as specific high level goals as a fidelity. So we have to run a series of simulations to make sure that we close the loop. So first, normally we do is that we pull our layout into a electromagnetic simulation tools, and then we simulate what kind of electromagnetic performance, or we simulate the Maxwell equations to reduce this kind of circuit into the circuit model. So after we having a slightly more abstract circuit model, then we can try to convert the circuit model to a quantum model that consists of Hamiltonian. And then with this Hamiltonian, then we can run the numerical simulations to simulate the time dynamic of the Hamiltonian, and then to check whether the operations we want the operations we hope is really the operation we want, and then determine what we have to change in terms of the design. So what I'm trying to say is that we have some high level goals to optimize the fidelity, but it's not immediately that apparently it's not immediately transparent to convert the high fidelity to a design layout. So a more transparent or more intuitive way is that we just simulate we just follow these multi-scale simulations, and then we simulate the fidelities with a given design. So we can just do this, and then after we simulate the fidelity, and then we kind of look at where we want to go, and then we change the design again, and then we complete this loop. So the most important part is that we want to close this loop as fast as we can, as efficient as we can, so we can run this simulation automatically and efficiently before the time is too long. Okay, so in our house, so we build the in-house EM servers to do this step, convert this circuit diagram to a circuit model, and then we have a recently published papers to remove free modes in the electrical quantum circuit, and then to do multi-couplings to efficiently reduce an arbitrary circuit to the Hamiltonian model. And then we also build the in-house evolution solvers to show the time-dependent simulation of the time-dependent evolutions of Hamiltonian to simulate our performance of a quantum operation. So with these two components together, so we actually close the loop of doing a fast and the fast design. So that helps us to verify all our circuit components very efficiently before we start doing the experiment. And this is actually the work done my colleagues team, so Huihai, and next time if we invite him to give a talk, he probably will go into details and talk about all this stuff. But here I'm just telling you that yeah, we have these in-house capacities to help us to design chips before we actually make them. Okay, so with all these tools in hand, and then we go on to build or we go on to build our Fluxonium in the processor. Okay, so previously I already introduced you about what is a Fluxonium. So it's actually still a simple circuit, but a little bit more complex than a charge qubit or transmon. So it has a Josephson junction, a capacitor, which is shown in blue. The Josephson junction is shown in red, and superinductance, or you can just call it inductance. You can call it just inductance. And here the inductance we usually make it by a Josephson junction arrays. So this is a loop consists of like 100 Josephson junctions. Okay, and then by having this circuit, so we also introduce some external control knobs that help us to read our circuit, control the circuit, and then do anything we want. Okay, so this is the layout of our chips. So you can see that there are two qubits in the middle that's capacitively coupled to each other, and then each qubit is coupled to its readout resonator, and then it has also individual flux drive line and the charge drive line, so we can control the charge degree of freedom or the flux degree of freedom individually. So here and we draw it as a source that's capacitively coupled to the qubit or inductively coupled to the qubit versus via mutual inductance. Okay, and next is yeah, we design the qubit, and then the qubit spectrum is the one as I described. So it has a flux dependent. So it has a flux tuning knob, so we can tune the flux inside the qubit to tune the frequency of the qubit. And then this is what we test in the experiment. So the qubit has its 0 to 1 transitions, so the ground to excited transitions that's spanning from a few gigahertz to something around 1 gigahertz at the flux, the half flux contact spot. And this is where we normally operate the qubit, because this is where the qubit has low frequency, it has long coherence, and at the same time it's kind of insensitive to the flux noise, so it both have the best T1 and T2 times. So normally we operate the qubit here. And then here we can see that the G2F transition is the ground to the second excited transitions are very far away from the 0 to 1 transition. So it gives us our qubit a really good two-level approximation that that means that it's a good two-level system. And then this will help us for operating the qubit a lot. And then our resonator, which used to read out the qubit, is actually very far away from the qubit frequency. So it's about somewhere between 6 to 7 gigahertz or even higher. So this is the qubit. This is the resonator transition frequency, and it's very far away. And then, but I will show you that it's not really the big deal in terms of reading out the qubit. Okay, and it's actually advantages of having them to be so far away. Okay, so now I already introduced you the architecture of our qubit and how we designed it, and then I'm going to switch the gears to introduce you how do we fabricate it. So here we can see that the qubit is actually it's more complicated, but it's not really that complicated. It just consists of two parts. So one is the capacitor, and the other one is just some junction. So in some sense, it's not really that different from a transmon qubit. So next I will show you that how do we optimize the part of the capacitor and the part of the Josephson junctions, so that we make sure that we make qubits. And then the first part is that we spend time to optimize our material growth and the fabrication technique of the capacitor. So in superconducting qubits, in terms of making long coherence times, a common practice people do is that to make the circuit simple. So to make capacitors, we just made two pieces of metal hanging inside the sitting on the very crystallized clean substrate, and then relying on the electromagnetic fields inside the free space to form the capacitor. So that really means that making high quality material and high quality interface is very important. So here I show you that we choose titanium nitride as our superconducting material, and then optimize the surface quality and the bulk quality of the material. And in the XRD rocking curve, then we have a very narrow free width half max bandwidth of 0.0838 degrees. Which means that which is a high degree of crystallized material we obtain. And then from the TEM image, that we can see that the interface between the titanium nitride and the sapphire is it's very clean. So there is a very small thickness of interface layers, and then there is no other ingredients inside the interface. But ensure that so we are able to make very high quality resonators and very high quality transmon qubits that indicating the high quality material and interface was achieved. So here it's data of our superconducting resonator made with a 6 micrometer gap. So and then the metal is titanium nitride, and then the substrate is sapphire. So the average Q at very low power, so at single photon level, it's about 2 million, with the best quality factor greater than 3 million. So it's really high if we consider the participation ratio of the device. And then at the same time, we make it a transmon qubit, and then so in this transmon qubit, we only make the superconducting metal pads using titanium nitride, and then we still make the junction out of aluminum. So by scaling all these qubits to 5 gigahertz, so this is the data of like 13 qubits, and then we got an average T1 of like 191 microseconds, so almost 200 microseconds. This is after we're scaling all these qubit frequency to 5 gigahertz. So that's this to indicate that we really do a good job in terms of making sure that the capacitor is of very high quality, and then left with the Josephson junction or the junction array part. where we have about 100 Josephson junctions for each qubit. Here we invented a new fabrication technique, so we can do this two-step shadow evaporation on the wafer scale. So normally people would think that this shadow evaporation is quite sensitive to the projection angles, and then it's pretty hard to control on the large wafer. And here we use a method that follows from the Manhattan kind of technique, which is invented a long time ago for fabricating the small junction and the junction array together. So here then you can see this is our qubit, and then the cross part is our small junction. The junction I colored red in the previous slide, and then so the square part, or how do I say that the glassy type, so the sunglass type structures, the connected sunglass type structures are the Josephson junction arrays that's fabricated within the same method. So by using this technique, so we are able to reach a wafer scale yield of almost 100% on the 4-inch wafer, with variations across the wafer within the 15%. So by selecting the chip cleverly, so we can actually make our chip very we can fabricate the device very close to our design target. So currently we can make the parameter variations within 10%, and then we're still working on improving that. Okay, so this is the fabrication about the junction array, or the junctions. And then with these two components together, so we put together everything and then checked how our qubit perform in terms of quality. And then we know that the quality. So to check the quality, it's better to take to measure the coherence times, the energy relaxation, and the diffraction time. Here is a typical qubit spectrum. So at the flux sweet spot, so the 0.5 flux quanta, where we have our qubits at low frequency. So this one is roughly around 1.1 gigahertz. And then that's where we operate the qubit. Then we measure the coherence times around this point. So for this qubit, so we get around T1 and T2 times, both above 100 microseconds. And then we can, if we go away from the sweet spot, then we can see that we maintain a high T1, but the T2 drops because of the flux noise. This is totally anticipated. Oh, okay. So by calculating the dielectric loss, which is always regarded as one of the most important loss sources of superconducting qubits, so we can deduce effective dielectric loss tangent of smaller than 10 to the minus 6. So this is actually approaching the state of the art number, although our qubit coherence times it's on the order of 100 microseconds. So this is you might ask why don't we get so we get a very good dielectric loss tangent, but why don't we get a millisecond coherence time like the others? So this is by choice. So we choose to operate our qubit on this particular frequency, which is still, this is much lower than transmon qubit, but much higher than a few other groups working on Fluxonium, because we actually optimize the qubit parameters with the coherence times taken into account. So yeah, we choose to operate these parameters because we think that's the best for performing gates. Okay, but in terms of dielectric loss, which is an absolute, more absolute metric of telling how good the qubit, how good the material is, so we're doing really good. Okay, and then we can also check the uniformities across multiple qubits. And then this is a 4-qubit chip, so we have two pair of 2 qubits located on this qubit. And then we find that we can find that so almost all the qubits has average T1 greater than 100 microseconds. And then we also draw the loss tangent calculations. sorry, the T1 calculations from a given loss tangents for all these 4 qubits. And then we find that it is remarkably uniform with the average loss tangent or the upper bound of the average loss tangent roughly around 1 times 10 to the minus 6. So this is this is quite promising. So it really indicates that the qubit performance and the quality is quite good. Okay, and then lastly, I'm going to show you a little bit about the dephasing at the fast space spot. So previously, then I showed you that the relaxation and so the T1 and T2 times are quite long, so about 100 microseconds at the flux space spot, and even away from the flux space spot, and then we can have a reasonably high T2 times. So here we can see that away from the space spot, the T2 times drops, but on most of the parts is still greater than 1 microsecond. So this helps us to deduce the flux noise amplitude. So in our case, our average flux noise amplitude is like something like 10 to the 5 times 10 to the minus 6 square 5 knot per square root hertz at 1 hertz. And then we test a lot of samples, and then this is the average values we get, which is in the range of normal levels of a superconducting device. And here I also want to note that although the T2 times doesn't look very fancy at the flux sensitive point. So for example, at here, the T2 times basically at just 1 microsecond, but this kind of behavior also indicates that it is 1 OIF flux noise dominating our T2. So so this kind of dephasing or this kind of noise can be suppressed by dynamic decoupling. So it's in the end, it's not that concerning. So this noise will reduce T2, but it's not that concerning because it will be removed by dynamic decoupling. Okay. So that's about the coherence. So I show you that the coherence times at the space spot are high, and then the flux noise are normal, and then we can remove the flux noise. In principle, we can remove the flux noise by using other methods. So it's not a big concern. So up to now, that I show you that we have very good coherence, and then we'll go on to operate our qubit to show you that we can operate the qubit as and use it as a resource for quantum computing. Okay, so the first is about readout, because if you want to do anything about the qubit, then you got to read it out first. And then here we designed our qubit readout resonator at a frequency of 6 to 7 gigahertz. And then we still use standard dispersive readout. So one may ask that your qubit is run at 1 gigahertz, and would the readout be very weak when the resonator is at 6? It turns out that it's not. So it's because the qubit has many higher levels, especially the 0 to 3 level transitions is actually quite high. So it's actually in the region of 7 to 8 gigahertz. So if we design our resonators in the 6 to 7 gigahertz, so we can actually utilize the higher levels of the qubits to perform the readout, but not substantially impact the Purcell induced, so the resonator induced decoherence of the qubit. So we actually it is advantages of using a lower frequency qubit in terms of readout. So this is our experimental data, and then we show that we can measure the dispersive shift regarding according very close to the design value, and then we can perform the high fidelity readout. So here the readout fidelity, if we just extract the projection, the preparation and the projection, and then it's only about 75%. But we have to know that our qubit is actually in a lower frequency, so our preparation without reset is not going to be perfect. So then this readout fidelity 75% is actually messed up by by the qubit symbolization. So next, we actually build the methods to actively initialize the qubit using the sideband queuing. So the way we perform the sideband queuing, it's simple. So we first use the flux pulses to move the qubit away from the symmetry spot to open the transition matrix element between our qubit excited state to resonator. And then so because of the resonator, it serves as a lossy channel. So after we pump this transition, so the qubit will decay back to this ground state. So by just keep pumping the green transitions, we can actually reset the qubit to the ground state very efficiently. And here we find that the resetting time is between 200 and 500 nanoseconds. And after doing that, we can have a reset fidelity greater than 98%. So this is just a lower bound. So the true fidelity is much higher because our characterization is limited by readout. So at the same time, we can tell us that our readout fidelity is also approximately 90% without using an amplifier, just supplementary amplifier. Okay, so finally, I want to say that this scheme can be multiplexed, such one microwave can be used to reset multiple qubits. Okay, so it looks like I'm a little bit slower than I expected, so I'm going to speed up. For single qubit operation, it's easy because it's actually not complicated because we don't have to worry about higher energy levels like transform qubit. So we only have to correct for 3 types of errors. One is for a phase errors induced by AC Stark shift. The other one is this over rotation errors, which is the amplitude error we called, and then the third one is called the axis misalignment errors that cannot perfectly align the x and y rotations. So by correcting these 3 errors in sequence, so this series doesn't mess up each other, we can demonstrate that so the average fidelity of single qubit gate to be 99.96%. 99.96%. So that's the average fidelity with some mediocre T1 and T2 times reached by some of our old qubits. So we believe that with our new qubit with greater than 100 microsecond T1 and T2 times, we can realize by 4.9 fidelity for single qubit. Okay, so currently the gate fidelity is limited by the coherence time, so still have quite some room for improvement. It can go beyond 4.9. Okay, and then lastly, which is the most and probably the most important part of the most tricky part is the 2 qubit gate, which is always considered to be the most difficult one to perform. Here we choose a 2 qubit gate. So here we use an easy way to perform 2 qubit gates, which is by tuning the resonant frequency of the 2 qubits together. So by doing that and then wait for some time at the anti-crossing point of the 2 qubits, we can actually swap the populations between qubit 1 and 2. So here this is the chevron swapping patterns between the 2 qubits. You can see that we are measuring the population of the first qubit in the 1 state and the second qubit in the 0 state. You can see that by sweeping the waiting time of the qubit of the second qubit on this spot, we can swap the population of the 2 qubits back and forth, and then this is not just a simple swap. It's a swap with a phase I. So it's an I swap gate, which consists of a universal gate set for 2 qubits. And here we can show that from the swapping frequency, we can show that the transverse coupling between the 2 qubits between 5 and 10 megahertz, and then that allows us to realize fast gate. So I kind of lose my mouse. Okay, never mind. So that allows to utilize realize a fast gate which has a 25 to 50 nanosecond gate time at the speed limit of the coupling. And then the gate is also performed inside the computational space, so it doesn't actually suffer. So it utilizes the energy relaxation time, the high energy defacing time. So the qubit defacing time of the Fluxonium inside the computational space. And certainly it's a simple scheme, so it's easy to realize. So to characterize that, we perform the randomized benchmarking and the interleaf randomized benchmarking, and then we show that the iSwap gave fidelity between our two qubits is 99.51. So that, to my knowledge, is the highest fidelity of two qubit gates realized in the Fluxonium system. Still, we still have quite some room for improvements because it hasn't already catch up the state of the art of the transmon yet. But by analyzing our errors, so we're still limited by coherence. So you can see that more than 0.25% of the errors are limited by the coherence, and then we believe that we can improve that, and then our current qubit is much better than this one. Okay. So finally, that's my summary slide, and the one I really want to conclude. And here the main message I want to tell is that we're focusing fidelity, so we want to reach a high fidelity first, and then even reaching a high fidelity, it's a systematic effort. So it really requires all the components work well at the same time. So it's never less difficult than just scaling up the system. It's also very hard. And then to do that, I show you that we have the quantum EDA tools. So it's a quantum design automation tools we develop in-house to help us to simulate the design before we perform the real experiment. So I show you that we are able to make very high quality material and robust junction fabrication methods to make our device. And then I show you that we can make a high coherence Fluxonium qubit with T1 and T2 times greater than 100 microseconds, which is compatible with a fast gate. And then the reset gate and readout are all demonstrated, especially the two qubit gate fidelity reaches 99.5%. And then the whole circuit scheme, it's based on the circuit-QED architecture, so it's compatible with scaling up. So finally, I want to give some perspective, and then we believe that we already have we are confident, and then we already have the technologies to demonstrate higher fidelity. But we really have to work hard to make them work all at the same time. Okay, so finally, so this is about what we are going to do next. So I already tell you the message that we are focusing high fidelity. So the hope is that we can go below 10 to the minus 3 in physical errors first, and then kind of a small trying to testing small scale quantum error correction tools to see whether we can reduce the logical errors. And then gradually we're moving towards building the logical qubit and then many logical qubits. So that's what we are trying to do. And then we have three major parts working together in our group, which is the experimental group that I led, and the system group, which is led by Deng, and I know lots of you are friends with him, and then the design automation group led by Hui Hai. And then we are eager to collaborate on all the critical areas, and then you can learn about the program at this website. And finally, we're hiring. So you can use this QR codes to see our job description, and then you can also send your inquiries to this email address. Okay, so I'm out of time, so I will take questions.